This conference will now be recorded.
Tawfiq, right now we do see a majority of your blue screen desktop, and at the bottom it's PowerPoint.
Yeah, I'll turn it into full screen whenever you guys ready for the presentation. Let me see. Let me turn my camera on too.
Okay, do you want to start? I think it's 7 minutes past, and hopefully everybody that they had the intent to arrive, they already here. And I'm gonna basically start the recording.
So let me turn it into a full screen. Let me see if I can get rid of that small thing here. That wouldn't. Oh no! I don't want to leave the meeting. Do you know how I get rid of it? From my screen, at least. Minimize it, maybe. Oh, okay. I got rid of it now.
Right. Do you have one screen on your end? Or yeah, now it's better. Thanks.
Yeah, I can see it now. Okay, so you folks can see what I have?
Yes, we can. We can see it.
All right. Well, thanks for the opportunity to present. I've been talking to Bobby about this for a little while. So the topic for me today is data center energy efficiency, and particularly, I think there's some opportunity for chiplets to improve that. So I'm going to talk about it a little bit. Now, let's talk a little bit to give you my biography. So I spent quite a bit of time, well over 20 years at Intel, and my focus was energy efficiency for notebooks, laptops and desktops and so on. And then I spent 2 years at Microsoft. I worked on the same topic except for data centers. And today I have my small consulting company doing also some projects, particularly with Oregon State, Intel, and some other folks working on, if you like, research again in data center efficiency. I want to acknowledge all the people who helped me with this presentation. From the board of advisors of my own company, and people from Intel, Stanford University, and Oregon State. All right, moving to the next one. So here's the flow of what I'm going to talk about today. And by the way, feel free to, interrupt and ask, because I prepared for half an hour, but I'm not sure. I may be the only presenter today, so feel free to ask anytime, to interrupt me. So the agenda goes as follows. First, I want to talk about the power vectors for data centers and the chiplet opportunities. Then a little bit of learnings from the client world and how we can apply some of these learnings to the data center. And finally, maybe my preferred top, if you like, 10 research and development area for that topic. Okay, so let's start with the power vectors for data center and chiplet opportunities. Okay, so that really, when it comes to power, if you like, three, at least the way I'd like to summarize it, three main vectors, okay? The first one has to do with peak power at any given time, basically. And typically what determines that is performance. It's the drive for performance. To a large extent today, the peak power determines, if you like, how many servers can you put in a given data center. So it is very, very important. It is that one thing that makes you decide potentially to go between one data center or two data centers, okay? So we can't talk about really peak power without talking about performance. And of course, I'm going to show you a graph that I borrowed from my colleagues who have presented at OCP multiple times. I'm not surprising you. I'm sure you all have seen that. But you can see on the left side what I'm showing here. As you can see, pretty much the frequency and the single-threaded performance has been saturated. And that's what people refer to as the slowing, of Moore's law. The number of transistors, however, you can see it still keep increasing exponentially. And same thing, power has been also, typically also saturated around the 100 watt, maybe per centimeter or something like that. So people have turned to this heterogeneous integration, which is what this group is all about, basically to get around that, to get around the fact that transistors, are not providing the power, efficiency, and performance scale, that we got used to, if you like, 10 years ago and so on. And because of that, there's a lot of complementary methods, obviously accelerator, other things, but even things like improvement in thermals, power delivery, and power management today, I think make up quite a bit of that performance chunk, much bigger, if you like, than what the generational technology, generational improvement you get from transistors. You get a lot more if you do a better power management or power delivery. And let me show you some examples, and that also related to the chiplet world. So let's look at power delivery. Okay, this is just a very, very simple example. If you have something like, on very gross power delivery, like on the left side, that's one extreme. And here, like I have an example of 100 cores, and I'm, supplying voltage to these 100 cores through a single VR. And let's say all cores are running at Vmax of the process, meaning everybody is running, and if you're on a single plane, for example, if you have one core that is in turbo mode, that one core, if you're on a single plane for power delivery, it's going to drive every other core to Vmax. So by definition, in a configuration like this, which is an extreme, basically, you have one core running Vmax, all cores running Vmax. Now, let's say I split that into just, two chiplets, each one of 50 core, each one have its own VR, okay? And now let's say half of the core run Vmax, and the other half is running Vmin. And you can do that, like in the first case, even if you have a single core running Vmax, everybody is going to have to run at Vmax. Okay, now I split them into these two chiplets, and I'm running those chiplets basically at the two extreme of the process. One at Vmax, those workloads that need very, very high performance. And on the other hand, I'm running the other half at Vmin of the process. And these are the workloads typically that don't need that much performance. They're running at a lower performance and lower power state, okay? Now, some very, very simple calculation. Typically, power varies with VQ, voltage Q. So you have one half now of those cores that's going to consume 1/8 of the power. And the other half is going to stay the same. So in that very extreme, you saved over 40% of power. Now, it doesn't go exactly like this because there are LDOs, and if you're on an Intel process, they use fiber, and And so it's never that much saving, because they have still, some control, some level of control to each individual cores, and you can do things basically. But even with fiber, if you like, even with LDOs, all of that stuff, I would say you're going to save about 20 to 40% of power. Now, if you go and do 4 chiplets, you get more savings. And you also get better distribution of voltage across these chiplets. One may be Vmax, one may be Vmin, one may be in the middle, and so on. And you get the idea. So basically, you get quite a bit of power savings if you move to this finer grain power delivery. And if you take it to an extreme, theoretically, what if I could have a VR, quote unquote, to every core? Okay, then that gives you the maximum fine grain, maximum power saving, maximum granularity, but obviously that becomes extremely difficult from a physical design perspective. Any questions so far?
What's the VR stands for on the slide?
Oh, voltage regulator.
Oh, okay, thank you.
Like a DC to DC, voltage converter.
So Tawfiq, this is somewhat similar to like DVFS, right? Frequency scaling with the frequency needs. So performance-based voltage scaling.
It's related. The implementation, the power delivery implementation, does impact your ability to do the DVFS, and I'm going to talk about it a little bit more in detail next lecture. My
Excellent.
very next bullet.
Thank you.
My very next bullet. You're welcome. So that's the first vector. It's the peak power. I think that's what drives things like what I've shown. Hey, I may need better power delivery. I want to put more chiplets and that kind of stuff. And obviously, interconnect, packaging, thermal management, all of that is basically has a very big impact on peak power. Now, after peak power, you have average power. Average power is basically, like it said, it's the average power. So you may be spending very, very little time in peak power. And most of the time, maybe you're not doing much. So you're looking at the average power, basically over time. And the biggest impact, if you like, on average power is the electric bill, because that's directly generally proportional. Today, it's not exactly proportional to the power bill because it's more complicated formula. But you can assume in a few years, people will figure out a lot of things, and it's going to be directly proportional to your electric bill. So it impacts your TCO. And the average power generally is quite lower than the peak power. Depends how well your utilization and all of that stuff. I would say it's, could be well below 50% of your peak power. And it's a domain of power management. Okay. Things like, I think the question was just asked, how do you do DVFS and the effectiveness? Well, DVFS obviously impact a lot of average power because you're scaling the voltage down, you're scaling the frequency down anytime, supposedly, you don't need the performance, right? And that's going to impact your average power quite a bit. So things like port state, system states, all those states and, clever design around them is what's going to give you, if you like, an average power. And to answer you even more, a little bit more about DVFS. So DVFS was created in the client world. And it's pretty simple. If you're one client, I have full control of my, if you like, laptop. And if I'm running low performance workload, I just scale both voltage and frequency down. If you scale linearly, if you scale only frequency, you get a linear decrease in power. I decrease frequency by 10%. Decrease voltage by 10%. I decrease frequency by 10%. I decrease power by 10%. But if you also decrease voltage, then if you decrease frequency by 10%, power goes cubical, and you increase power, you reduce power by well over over 20%, which is why people do DDFS. But if you're a single client on a laptop, that's easy, right? Because you have full control. Now, if I have in a data center world, if I have two customers sitting on that voltage plane, and one customer, running very low workload, and where I want to go down in voltage, reduce power, but there is that other customer that wants to go up in voltage because he's running turbo. And for me to deliver the performance to one of them, I have to increase voltage for both of them. So DDFS becomes a lot more complicated generally, to answer your question, in a data center world, in a multi-client world on the same processor. Except, like I said, if you can go to an extreme and control every core independently, then maybe you can give each customer what they want somehow independently. But again, the physical design becomes very, very difficult. And the third component is the idle power. And that's the domain of low leakage devices, because most of your power here is leakage, or should be leakage. If you're doing good power management, the only power you should be spending when you're idle is leakage, okay? And how do you go, and manage that? Any questions so far before I move to the next slide? Okay, so I can move. So let's look a little bit about the learning from the client world and a little bit on the difference between client and the data center. So I'm showing here, this is about maybe 25 years ago, what the first laptop used to look like. And maybe on the very right, how it looks like today. And it really took about 25 years to get from the left side to the right side. And I'm going to show a little bit of the kind of drivers that led to that, of course, was an eye on how do we do something similar for the data center. And you can see today, for example, if you look at this curve, I know it's hard to see, but it plots performance versus, TEC. TEC is a total energy consumption, and it's mostly in the off state. You look at the energy when you're not doing anything. It should be very, very low if you're doing a good design. And you can see how performance has been improving very significantly, at least relative to the energy you're spending in the off state. And the right-hand curve, you can see, if you like, the CO2 footprint decrease, similar exponential decrease in the laptop space. So the question, how do you get that in the data center? So let's look at some of the differences. So on the left, you have the data center, okay? And on the right is actually, I'm sorry, on the left is on laptops. On the right is the data center. So if I look at just idle power in laptop, today is a very, very small percentage of total power, typically less than 1%. Because it took 25 years, but people figured out how to quiet that laptop. If you're not doing work, we know how to put everything in an idle state, basically. If I look at a data center and say, okay, if you have a core, that's not doing work, what's the percentage of leakage on that processor overall? It's actually significantly higher. It looks like what mobile used to look like about 20 years ago. So clearly there's a lot of room for optimization, for idle power at least. And if you ask, what are the reasons basically that's happening, okay? If you look in the laptop space, you reduce idle power, you reduce idle power for a reason, which is primarily battery life. And battery life is a user experience metric. People buy laptops based on battery life, okay? But power bill in a data center is not directly something visible to the consumer. So there's no motivation, if you like, similar to what was on in the laptop space. Another user experience, for example, is like modern standby or airplane mode. If you leave your phone, you come back in a month, and that phone is still, still has battery, operational. But idle power is not a visible. Again, it's not a visible metric in a data center world. If we talk about benchmark, there's another big motivation, which is something like Energy Star. And Energy Star keep evolving and kept evolving, and every year, you raise the bar. And like I showed you before, in the previous curve right here, it really defines, for you to get that label, that's Energy Star, it defines how much power you can spend when you're in the off state, meaning when you're not doing anything, basically. And that, of course, drives silicon vendors, drive the laptop manufacturers, everybody, to go and reduce, if you like, reduce that energy so they could get that label, because people attach monetary value, to that label. There is no equivalent thing like this in the data center world. If I want to go and buy a virtual machine, from Microsoft Azure or from Amazon, there's tons of data that compare the performance of the two, EC2, versus whatever from Azure, and you can look at performance benchmark and decide what you need. But there's nothing that says which virtual machine is actually spending less power, and or causing other customers to even spend even more power. There's no such standard. So that's actually makes it harder for the big cloud providers to actually go and spend a lot of effort and a lot of money to reduce that idle power. If all they have to worry is about the electric bill, it's much less of an incentive than we had on the mobile world. Any more questions, folks, before I move?
What percentage is, when you say idle power is a small percentage, I don't recall if you gave a number, what percentage is it of the total power?
I didn't give one, honestly, because I think it varies. It varies, and I don't know. I have some ideas. I have seen some companies. I don't know what other companies are doing specifically. They tend not to publish that. But if I have to guess, if I have to make an average guess, I would say somewhere between 20 and 50% versus the 1% or less in the mobile world. But some companies spend more time around that, and I can't tell really. I can't tell. It's not something that's published.
Okay, thank you.
Sure. Other questions before I move to the next one? All right. So yeah. And by the way, to answer even the question a little bit more on the DVFS, if I go back here, and how power management can help, like if we go back here, in a world like this on the left, where I have a monolithic die, and let's say a monolithic plane where I'm supplying that voltage, my ability is very limited to do a DVFS. If I have something like this on the top core on the right, and I have some smart software that knows how to partition workloads, between those different cores, then I can just, partition the lower performance demanding cores on the lower planes and still do DVFS on them, independent of the top chiplets, if you like. And again, if I have every core, now if I have individual controls in the ideal sense, let's say each core has its own VR, 100 cores, then I can do DVFS on each core completely independently from the other cores. So you get much, much better average power. So you can see that physical implementation, the power delivery, physical implementation is very, very, very key to a fine-grained power management. Okay, so now I'm almost toward the end. So let me see what I think, the top, if you like, 10 R&D, areas. And I'm working, we're working some of that stuff a little bit with Oregon State, and some other folks from industry. But the top one for me, at least for the power efficiency, is that first bullet. And I split them into three main ones. One on physical design and power delivery, the other on power management, and the third one on standard. So on power delivery, fine-grained power delivery to individual core is very, very, very key. Now, Intel does that. They have something called fully integrated voltage VR, or FIVR. It may not be exactly to individual cores. It may be like, every 4 or 5 cores have their own domain, but they have that. And they design those voltage regulators with a, leading edge of technology, on like 3 nanometer, 5 nanometer. I have my doubt about the scalability of something like that, but there is already a solution which has some of that, fine-grained power management. AMD and others do that with a different technology, less power efficient, called LDO, low voltage dropout, simply an impedance divider, basically. And, it's a very complicated analysis to go figure out under what circumstances which one is more efficient. But ideally here, if we could have something very efficient, and we could have those regulators built, on the process technology as the rest of the chip, then you'd have very, very good, fine control, power management, fine control. The other one that's interesting, and to me that's totally in the research space today, is, hey, can I put 60 volt directly to the processor and do all the conversion all the way to sub 1 volt, in the processor? So I'm eliminating multiple stages of voltage regulators. And that's, obviously not an easy thing to do, but it's something that definitely should be, researched. So moving a little bit further, local hotspot cooling. So there's obviously a lot of research with liquid immersion, with different liquid solutions to actually provide better thermals. But there's a lot of also that can be done if you just cool the hotspot only. So maybe, because ultimately what you're trying to do is cool that silicon below its maximum operating temperature. And, if I have a 20 or 30 degree gradient on that die, the cache, the memory tend to be very cold. The ALU is going to be very, very hot. And that research has been done for 20, 30 years, but it has never, as far as I know, deployed in production. Basically something like the Peltier cooling, or, but I think it's worth it to take another look at something like that. And finally, I think low leakage device is very key for the idle power management. And that's something, by the way, that's not necessarily just data centers. Mobile devices, everybody wants that kind of devices. In power management, there's 2 areas, right? The first one basically is telemetry, because like if you want to do all these DVFSs, okay, for example, I really need to know what every core is doing, and I need to control them independently. So I need a telemetry. I need to know, I need to predict what the workload is going to be, and stuff like this. We need something that's a little bit smarter than the mobile space single client to algorithms that can deal with multiple clients, okay? And again, the chipless world is a little bit friendlier. The more I can split into chiplets, the more I can isolate, some of these clients from each other. And finally, the standards, there's, something equivalent like that Energy Star. Some standard, some benchmark, that can tell you, hey, this virtual machine from this vendor is more power efficient than that virtual machine, from that vendor. So this is at least in the, research area that I see that's going to be actually quite, I think, critical to get to some really sustainable and very low power, data centers, very similar to what, if you like, mobile did in the last 20, 25 years. And that's all I have, basically, folks. So.
Hey, this is Michael from Samsung. I have a question on the second bullet from on the power delivery and physical design. It says, direct single step conversion from 60 volt to sub 1 volt.
Yeah.
Could you, explain a little bit more on that? I'm trying to get some idea on this one.
So if you look, typically, and maybe I should do a whiteboard, but let me try without a whiteboard first. Today, in order to get from 60 volt to what the core needs, which is roughly half volt, typically you have 2 or 3 stages of conversion. Like you're going to go from 60 to 12 volt, if you're on Intel, you go 60 to maybe around 2 volt. And then you do the conversion from 2 volt to sub 1 volt inside the processor. Now you have 2 stages of conversion, so the total efficiency is the multiplication of these 2 stages. And let's say you get 85% on the second stage, maybe 90%, you end up with about 80% total efficiency. But somehow, if I could have some very efficient single stage where I don't need those VRs from 60 to 12 on the motherboard, I just go from 60 directly and put 60 volt directly to the core. So now you're putting 60 volt on an advanced process that typically today, is a 1 volt process. If you can do that, then you can miniaturize those VRs. You can get rid of the one stage from the voltage regulator and you can miniaturize the ones that goes from 60 to 1. And if you can do that with high efficiency, then you get everything you want. You get all that fine-grained control because now inside the processor, I have a VR for each core, and it's a very efficient VR.
Okay.
Is that clear, or you want me to try again? I can do some whiteboard if you like me to do that.
So basically, you try to remove that multiple, stage.
Yes.
I see. And I have, another question on the page 7.
Page 7. Okay.
Actually, all the way bottom, there's one line, a kind of a summary, right? The chiplet helps more consumer isolation, partition. Yeah, I want to see some insight, between this two-world PC versus the server in the data center. What's the I want to see the more clear on the last that one line sentence, what you try to deliver.
Sure. Let me go to this figure and maybe try to explain it. Now, these are, the left is an exaggeration, but it says, like if I am here, and let's say in a client or in data center, but I have a single monolithic die of 100 cores. And let's say I'm in a laptop space, for example, in this case, and I'm a single user. So now, and let's say all these cores are connected to one VR and one voltage plane, which means every core is going to be at the same voltage because they're connected to the same voltage, all the cores. But I'm on a mobile, I'm one user. And if I'm running something that requires low performance, I go and do this, what they call DVFS, dynamic voltage frequency scaling. Because I don't need the performance, you know, there's an algorithm there that goes and lower the voltage to these cores and reduce energy, basically, reduce energy very, very significantly. Now take that situation, same situation, but let's say you're in a data center world. In a data center world, the main difference is you may have 10 clients actually working on workload on that processor. Let's say every client has 10 cores. So you have one client, let's say, who needs performance, who is running turbo and want high voltage. You have those other 10 clients that don't need the performance. They want to do low voltage. But because they're sharing voltage, you have to go to the least common denominator. You can no longer do DVFS. I cannot reduce voltage anymore because then I also impact the client who needs more performance. So in the client space, because I have only one client, it's much easier to trade off performance versus, you know, energy all the time, and you do that automatically. In a domain where I have multiple clients sitting on that processor, I cannot do, you know, I cannot affect them. I cannot affect client A by what client B wants to do. So I have always to go to the least common denominator. And because of that, my ability to power manage gets much smaller. I can improve it if I do more chiplets and to start distributing those different clients more intelligently. And say, okay, the client who wants performance, I'm going to put him here. And the client who wants, you know, less performance, I'm going to put him here, and so on. So I regain a little bit better, you know, than what I have in A. But I'm still far from being able to completely manage it like I would do in the client world. I know it's a very, very long explanation, but I'm honestly very happy to start some whiteboard if you want me to go. You know, did I answer it? Is that?
Yeah. I kind of got that sense actually. I thought, you know, how we can actually apply the concept you show on the earlier slide for the data center, you know, power management.
Yeah.
I think with the chiplet approach, probably, you know, we can manage like based on the finer granularity in terms of power management. That will save, you know, the power for the data center business. Okay, great, thank you.
And by the way, here, where we really need something very clever, very new, is some algorithms that can figure out what workload to assign to what chiplet. If you can do that, then maybe you can start approaching what the client world is doing. But that's what's needed. You need.
I thought that, you know, in the data center, maybe, you know, when they receive the query from the customer, and then there's just some software determine this is like a, you know, some intensive work required, then we can direct to the like a high power consumption server, and then only, you know, make it work that server, something like that may save the power, you know, in big picture, I guess. Because of
Something like that.
Yeah.
Something like that. They need to go, to the core so they need finer granularity management on the software itself. But something like that, yeah.
Okay,
Sure.
great. Thank you. Yeah.
You want?
I have one question. This voltage regulator that you're mentioning, are those basically on-die voltage regulator or on package or on PCB?
Oh, that's an excellent question. So it depends which vendor. For example, Intel has an on-die voltage regulator, and it's usually not visible to you, but they have in-die voltage. It's called fully integrated voltage regulator, and this is where they do all the fine grain kind of stuff. But because, like I mentioned, typical silicon processes cannot deal with higher than 2 volt. You have a process designed for, a volt, half a volt. And you cannot just put a battery of 20 volt directly into that processor. You can always cascode, those voltage regulators, but then you lose efficiency. So because of that effect, they have another voltage regulator on the motherboard that goes from, say, the battery 20 to 2, and then you go from 2 to roughly 2 to something below 1. For servers, they may have 2 or 3, like go from 60 maybe to 12, 12 to 2, and 2 to sub 1 volt, always inside the processor. So I've seen, like on die, I've seen on the board. There are people who do voltage regulators on the package as well. And even when you do on die, there is some component of that voltage regulator on the package. So typically it's distributed. And if you take a different technology, like an AMD or maybe in the future ARM, I don't know, it's a very similar story, except the last stage that is on die, that is a voltage regulator, is not present. There is just a voltage divider there, which is a little bit less efficient to give you the granularity you need, so you could have multiple voltage control on the die. So the short answer, you have on the die, you have on the package, you have on the board. Typically, it's a solution, it's a cascade solution, and the efficiency is the multiplication. But the implementation varies from an Intel to an AMD to ARM.
Thank you. Can you maybe just in 1-2 bullet tell me what's the benefit of actually having it on package versus on PCB?
On package versus the main difference, the closer you get to the load, the more you remove of that load line or resistive path. So you reduce that. And of course, on package, it's more expensive because package is more expensive than PCB. It's more advanced. So real estate, is going to cost you more. So typically people don't like to do it there. And you have to deal with things like cooling. If you have a VR and, you have to cool it. And now if you have it on the package, well, you have to make sure, from a form factor perspective, you have to worry about things like, heights and stuff like this, so you can have a good contact between the processor, the voltage regulator, the heatsink, and all of that stuff. So I think because of that, I don't see a lot of people doing on package today, VRs. They tend to be mostly PCB, and of course there is the on die, portion of it.
Thank you. Thank you very much.
Sure.
Any more question from audience? Okay, if not, I think, thank you, Tawfiq. I think we have 10 minutes early to finish, but thank you. It was a great presentation.
Sure. Thank you.
Yes, thank you, Tawfiq.
Sure. Thanks.
Thank you.
Bye.
Bye.